Greetings. Our first lesson is semiconductor theory. Obviously, in our first lesson, we must introduce objectives, which are namely define terms, explain the electronic configurations of atoms, discuss the energy bands in solids. Understanding semiconductor devices such as diodes, transistors, and integrated circuits. So that's why it's good we understand this topic, semiconductor theory. An atom is the building block of all matter and is made up of subatomic particles. Electron, which is negatively charged. Proton, positively charged. Neutron has no charges. Atomic number, this is the number of protons. Atomic mass is the number of protons and neutrons. An element, a pure substance consisting of only one type of atom characterized by a unique atomic number. Silicon and germanium are such examples. I repeat, silicon and germanium are examples of elements. Silicon and germanium are examples of elements which you can find in a periodic table. And it's good to remember that the periodic table has periods and what we call the groups. So some elements can be found in groups and elements can be found in period. Molecule. A molecule is a group of two or more atoms chemically bonded together. A molecule is a group of two or more atoms chemically bonded together. A compound is a substance composed of two or more different elements chemically combined in fixed proportion, e.g. gallium arsenide and silicon carbide. Covalent bond refers to the types of chemical bond in which atoms share valency electrons to achieve a stable electron configuration. Electron configuration in an atom. This is the arrangement of electrons in an atom's energy level or shells around the nucleus. Or shells around the nucleus. Electrons moves in circular and elliptical orbits around a relatively heavy nucleus of protons and neutrons. The diagram shows an electron in an orbit, and this orbit in relation to the nucleus, we call it the first energy level. So this circle is an electron. Inside it, we have the nucleus. And the path upon which electron moves is called an orbit. Next slide. So, this is what we call the Bohr atomic model. Bohr atomic model. Postulate of Bohr model is that electrons revolves around the nucleus in fixed circular orbits called energy levels or shells without emitting energy. These orbits are quantized, meaning an electron can only exist in specific allowed energy levels. Number 2, the angular momentum of an electron in an orbit is quantized and follows the equation. The one is shown where m is the mass of the electron, v is velocity of the electron, r is radius of the orbit, h is Planck's constant, n is the principal quantum number. Next slide. An electron can move from one energy level to another by absorbing or emitting a photon of energy equal to the difference between the two levels. E, we have this equation. E is energy difference. H is Planck's constant. and this symbol is frequency of the emitted or absorbed radiation. Next slide. While in a specific orbit, an electron does not radiate energy despite being in motion. This contradicts classical electrodynamics, which predicted that an accelerating electron should emit radiation and spiral into the nucleus. So those are the four Bohr postulates that we have. Electron configurations in an atom continuation. So we have the quantum mechanics. This is where this knowledge is derived. And we have this equation 2 times n squared, where n is the shell number. The principal quantum number n is that the first quantum number is called K shell, the second quantum number L, and the third quantum number M, fourth quantum number N. All right, let's try. If we write 1 in this equation, 2 times 1 squared, we get the answer is 2. So the first energy level has a maximum of 2 electrons. The second energy level is 2 times n raised to power 2. That is 2 times 4 is equals to 8. So the second energy level has a maximum of 8 electrons. Third energy level, 2 times 3 raised to power 2. That is 2 times 9 is equals to 18. The fourth shell is 2 times 16, which is a total of 32. Right. We have the valency shell and we have the valency electrons. These are terms we shall encounter as when you go. We are going to look at the p type and n type, or again when we shall be looking at energy band diagram. What is this? Valency electrons are responsible for conduction of current. Now, this is an illustration of an electron configuration whereby we have the first shell, the K shell, a maximum of 2, that one and that. The L shell has 8. The M shell has a total of 18, and the N shell has 2 times n raised to power 2. Silicon, crystalline atom. So we have now covalent bond, and remember covalent bond is the bond formed by pairing or sharing. They are sharing some electrons to achieve a stable configurations. So the shared electrons are these. and silicon consists of an atomic number 14, which is the number of electrons. So that's its electron configurations, while this is the crystalline structure of silicon. Energy band in solids. Electronic materials are classified into the following: conductors, insulators, semiconductors. The valency band, forbidden energy gap, and the conduction band. The top is the conduction band. The middle, this is the forbidden energy gap. And then we have valence electrons. Valency band, it is the band of energy occupied by the valency electrons and is the highest occupied band. It may be completely filled or partially filled with electrons, but never empty. Conduction band. This is the next higher permitted band and may be either be empty or partially filled with electrons. Electrons move freely in this band, hence called conduction electrons. Band gap. This is the gap between conduction and valency band. Note: if a valency electron happens to absorb enough energy, it jumps across the forbidden energy gap and enters the conduction band. An electron in the conduction band can jump to an adjacent conduction band more readily than it can jump back to the valency band where it had come earlier. When an electron is injected from the valency band, a covalent bond is broken and a positively charged hole is left behind. This hole can travel to an adjacent atom by acquiring an electron from that atom, which breaking an existing covalent bond and then re-establishing a covalent bond by filling up the hole. It is to be noted carefully that holes are filled with electrons which move from adjacent atoms without passing through the forbidden energy gap. Summary: conductions, electrons are found in and flow freely in the conduction band. Holes exist in and flow in the valency band. Conduction electrons move almost twice as fast as the holes. Energy band diagram for unexcited and excited silicon. We have a curve of energy in the y-axis and x-axis for unexcited silicon. The first band consists of 2. Remember the formula 2 times n raised to power 2. So the first is 2, the second is 8, and the third is according to the principal number. This is for excited, and for excited, we means we have a heat supplied which is able of dislodging an electron, and the moment an electron is dislodged, we have a hole. And what is a hole? Is a positive electronic charge. So anytime an electron is dislodged, whatever is left behind is a hole. And we have a hole being left. So we have an electron. This motion shows a free electrons being dislodged by heat. Remember, heat energy. Energy is the ability to do work. That brings us to the end of this lesson. Our sources are as listed, and we acknowledge electronics notes are electronics tutorials for their materials. Assignment 1. What is a semiconductor? Give 2 examples of elemental semiconductors. Define intrinsic, extrinsic semiconductors. Differentiate between a conductor, semiconductor, and insulator in terms of the energy band structure. And what is the energy band gap of silicon? So it's me, Mwalimu Ngigi, and that brings us to the end of our first lecture, semiconductor theory, a very interesting topic as far as electronics is concerned. So subscribe, like, and share to the video. Thanks very much. Bye-bye.